Hello everybody. How's it going? So welcome to this stream. We're gonna have some fun today. Now, before I go on, the first question, people had a lot of questions about one of the last assignment questions, specifically the very last assignment question. 22.56. Well, this one was from the last assignment, but people had trouble with it. I can maybe see why you would... Wait, no. 22.56. This is chapter 23. Oh, here, hold on. You know what? I messed up something in the description. I'm going to change this. 23.21. 20. All right. So, right. 22.56. That question goes... Okay, it goes like this. An XYZ coordinate system contains three charged particles. Particle 1, minus 5 microcoulombs at 4 meters, minus 2 meters, 0 meters. Particle 2 is at... it has some charge at some other position. And there's a third electron. Okay, so it says draw a diagram showing the vectors you need in order to determine the direction of the separate electric forces exerted by the electron on the electron by particles 1 and 2. So I'm not sure what it is about this people had trouble with. My guess is that it's how it's in 3 dimensions. So before I go, there's two things I want you to know. One is that the method I taught you in class, it works for any number of dimensions. So if I give you a 6-dimensional vector and said, hey, the vector from A to B is equal to 4 I hat plus 3 J hat plus 7 K hat plus 9 L hat plus 27 W hat, whatever, right? The procedure would be exactly the same. First, you find the magnitude of whatever this vector is using some convoluted Pythagorean theorem. And then you would find R hat 1 over RAB times RAB, and continue as you normally would. So that's one aspect of that. Maybe you didn't know that. I wouldn't lead you wrong. One of the reasons I tried to teach you a method that was as general as the method I taught you is because it works in any number of dimensions. The second is that this actual question is in 2 dimensions. So that's nice. So let's set up our XYZ coordinate. How about as X is along this axis, Y is along this axis, and Z is along this axis. Okay. You'll note that particles 1 and 2 are both on the XY plane. So particle 1 is, let's just draw a thing here. It's at 4 meters minus 2 meters. 1, 2, 3, 4. 1, 2. So it's literally down here, Q1. Particle 2 is at 1 meters, 2 meters. So 1 meters, 1, 2. So it's up here. because they both have no z component, I can write their position vectors as so this one is 1 meter I hat plus 2 meters j hat plus 0 meters k hat, and our one is at 4 meters I hat plus minus 2 meters j hat plus 0 meters k hat. Okay. So then there's an electron at minus 1, 0. So the electron is over here. So the question asks us to find vectors. Well, hold on. You know what? I am going to move this whole diagram to the left, or to the right a little bit to make room. Okay. Be nice. Oh, whatever. Okay, so the position vector of the electron is going to be a minus 1 I hat, 0 j hat, 0 k hat. So the question asks us to draw a diagram showing the vectors you need in order to determine the direction of the separate electric forces. So the vectors we need are the vectors from Q1 to E, and this vector here from Q1 to E. So we'll call this R2E and this R1E. And these are the vectors I need to determine to figure out where they are. How do I determine their components? So that's something we covered last term, but you know, if you have a particle over here and a particle over here, and you know their position vectors relative to the origin, if that's the position vector of particle A and that's the position vector of particle B, you can determine the vector from A to B, RAB, using vector addition and substitution. So the idea here is the vector starting at the origin, going up to A there, and then down along this one, it takes you to the same point as going from that way. RB is equal to RA plus RA plus B. That's our way of saying if they all start at the origin, or if A and B start at the origin, this series of motions takes you to the same point. An alternative way of putting this is RB minus RA is equal to R A B. In other words, you have the point you're going to and the point you started from. If you subtract the point you're going to, or you take the point you're going to and you subtract the point you're coming from, you get the vector between them. So we can use that to calculate these two vectors. Boop. Delete. Also, you'll note something here, which is that all of these points are on the xy plane. So for simplicity, I'm going to leave these k parts in the system, just so I can show you the calculation, because I made a claim a little bit earlier that it doesn't really matter. As long as you have the vector components, you can do the procedure the same. But in this diagram, I'm going to delete the z-axis just to simplify things a little bit. All right, so we need to calculate R1E. And according to my description, that's RE minus R1. So you write each of these out. Minus 1 I hat plus 0 j hat plus 0 k hat minus 4 I hat plus minus 2 j hat plus 0 k hat. I'm going to make this procedure as explicit as I can. If you can do these in your head, congratulations. So this becomes minus 1 minus 4 I times I hat plus 0 minus 2 j hat plus 0 minus 0 k hat. Becomes minus 5 I hat plus j hat. What? Hold on. Oh, okay, yeah. So this goes 1, 2, 3, 4, 5 to the left, and it goes 2 up. And then there's 0k hat. Over here on the right-hand side, I'm going to use the same diagram to calculate R2e, that vector. So it's RE minus R2. So it's minus 1 I hat minus 1 I hat plus 2 j hat. So then you get minus 2 I hat minus 2 j hat plus 0k hat. Okay. I simplified that calculation a little bit just because I wanted to save some space. Okay. So the principle here is I want to figure out what the electric forces are from each of these, and then I want to calculate the vector sum from both force. So I'm just going to do a parallel calculation here. So just like I said, the first steps of these are to figure out what the vector between them is from the source to the thing feeling the force. And then you're going to calculate the magnitude of that force, which you use Pythagoras for. So it's minus 5 all squared plus 2 all squared plus 0 all squared, which becomes square root of 29. And then our unit vector is going to be our original vector divided by whatever this value is. Okay, so this magnitude is minus 5 over 29 square root I hat plus 2 over square root 29 j hat plus 0 over 29 k hat. Let me get out my calculator. So it's minus 0.928 I hat plus 0.371 j hat plus 0 k hat. Okay, so that's the unit vector in the direction of the force. And now I need to calculate the magnitude of the force, which is k q1 q e over this length all squared. So Q1 is, okay, so K is 9E9, and Q1 is minus 5E minus 6 coulombs, and the electron is 1.6 E minus 19 divided by the distance between them squared, 29 all squared, which becomes okay, 5E minus 6 times 1.6E minus 19 times 9E9 divided by 29. 2.48 times 10 to the minus 16 newtons. Okay. Now to find the force, I'm going to multiply 2.48 times 10 to the minus 16 times r hat 1e. So it's 2.48 times 10 to the minus 16 times minus 0.928 I hat plus 0.371 j hat plus 0 k hat. 2.48 e minus 16 times minus 0.928 minus 2.301 times 10 to the minus 16 plus 2.48 e minus 16 times 0.371 so that's in the I hat direction, that's in the J hat direction, and it's 0 in the K hat direction. Okay, so that's how to do the first half of this problem. Let's repeat it for this second one. So the magnitude, R2e, is going to be square root of 2 squared plus minus 2 all squared plus 0. So it's going to be the square root of 8. So R2e, the unit vector, is going to be, I'm going to divide minus 2I hat minus 2J hat. Is it really minus 2 minus 2? Oh, it totally is. Okay. So this becomes minus 0.707 I hat minus 0.707 J hat plus 0 K hat. All right, now it's time for KQ2 QE over the distance between them all squared. So it's 9E9. Q2 is 12 microcoulombs. And an electron is minus 1.6 E minus 19 square root 8 all squared. 9E9 times 12E minus 6 times minus 1.6 E minus 19. Wait, hold on. Let me redo that. I think I made a mistake. Times 12E minus 6 times minus 1.6 E minus 19 divided by 8. Alright, so that's minus 2.16 times 10 to the minus 15. And now I'm going to multiply these two together. Minus 2.16 times 10 to the minus 15 times our hat 2e. So it's going to equal minus 0.707. So it's going to be 1.52 times 10 to the 15 minus, in the I hat direction, 1.52 E minus 15 in the J hat direction, and 0 in the K hat direction. So these are each of the forces. This is the force of 1 on the electron, this is the force on 2 on the electron, and now I need to add them together. So now I just add the components of the vectors. Minus 2.301 times 10 to the minus 16. 1.52 times 10 to the minus 15. I hat plus 9.201 times 10 to the minus 17. 1.52 times 10 to the minus 15. J hat plus 0 K hat direction. So let me add these together. Get out my calculator. 2.301 E minus 16 plus 1.52 E minus 15. That's positive 1.29 times 10 to the minus 15 newtons in the I hat direction, and 1.61 times 10 to the minus 15 newtons in the j hat direction and 0 newtons in the k hat direction. Okay. So overall, this is just the same procedure that we were doing in class, literally step by step. Let's see if anybody's watching. Oh, 3 people are watching. Hello. If you have any questions, you can just ask in the live chat bar. I'll keep an eye on it as I do the questions. Well, let's move on to the next one. This is 23.21 modified. So the things and techniques and ways of thinking that we're doing these questions aren't entirely different from, we're involving concepts from previous terms, from last term. Like, I don't assume that you don't know anything when you come into this class. You should know, force vectors and stuff. So some of these questions involve them, and I couldn't find an analog that asks similar questions to question 21. So I'm going to ask you one that is similar. So suppose 2 plates lie in parallel, horizontal planes. One plate in the xy plane at z is equal to 0. The other plate in the plane parallel to the xy plane at z is equal to 10 millimeters. Between is a constant electric field directed upwards. A proton and electron are launched in the positive x direction with the same position 0, 0, 5.0 millimeters. So the halfway between the plates. If the electron strikes the plate at 300 millimeters, 0, 0 millimeters. All right. So that's the question. I've modified it slightly to make it different. So the first part of this question is like, how do you start parsing this? It might be nice if you get drawn a picture, but I'm not sure if you do. Essentially, here's a rough sketch. X, Y, Z, and you've got these 2 plates. Okay. This plate is on the XY plane. This one is parallel to the XY plane, but at Z is equal to 10 millimeters. And what you're doing is you're putting a positive charge and a negative charge in it, a positive charge and a negative charge, and you're letting them go, and they're going to feel forces. Okay? So drawing it in 3 dimensions is kind of confusing. So what I'm going to do is I'm going to look at like a horizontal slice, or rather, bleh. I'm going to take a little slice of it at y is equal to 0. Okay. So this is what it looks like along the xz plane. There is the x-axis is like that. Or sorry, the z-axis is like this. The x-axis is like this. And there is positive charges down here, told. And negative charges up here, because there is an electric field pointing up. And so the question is, okay, so you've got a little particle. You're releasing it halfway between them when z is equal to 0.5. So this here is z is equal to 10. This one z is equal to 5 millimeters. And you're taking a proton and an electron. You know what? Let me reproduce this picture here. Let's simplify things. Get rid of this. This over here. Copy it. Paste image. All right. So in the story, they're saying, hey, if you took a little negative charge and release it with some initial velocity going to the right, and then you do the same with a positive charge, and you send it moving with the same initial velocity. Okay. So how are these charges going to move? So the negative charge is going to feel a force pushing straight down, right? And we're told that this is a uniform electric field, which means that it's going to feel the same force throughout. So it's going to follow a projectile motion, kind of like gravity does. And it's going to end up at some point there. We're told what the point is. We're told that it ends up at point 300 millimeters. So that's at location 0.3 meters. That's where it hits. Well, how's the positive charge going to behave? Is it going to behave the same or differently? The positive charge is going to feel force. Which direction force? Positive charge is going to feel a force pointing upwards in the direction of the electric field because it's positive. So it's going to follow a path. Is the path going to be the same or the different than the path of the electron? Seems to me like it's going to depend on two things. One of them is how big the force is, and the other is going to be how strong the what the inertia is. Now we know that the proton and the electron have the same charge, so the forces are going to be the same in these cases, but the accelerations won't be, because the proton has a lot bigger mass than the electron. So what do and I don't know in this case? I have a sense of what the force is going to be, or I have a sense of which direction the force is going to be. I don't know how big the force is. I don't know how much force it feels. But if I did know how much force it feels, I could tell what the acceleration was. And the acceleration is going to have a 0 I hat component, and it's going to have some unknown j hat component. So, if I knew what the acceleration was, I could use, essentially, the techniques we talked about last term to figure out exactly where it's going to land over here. So the question is, well, actually, figuring out where it's going to land is going to depend on two things. One of them is what the acceleration is, but also it's going to depend on what the initial velocity is. given this information, I know that it's going to have some initial velocity in the I hat direction, so to the right. And also, I know that it's going to have that its velocity is entirely to the right. Yeah. So I need to figure out what this term is, and I need to figure out what this term is before I can answer the question, where does it hit the roof? So how do I figure those out? Well, I can figure those out because I know what the inertia, I know what the inertia of a proton is. So if I knew what this force was, I could use the inertia to figure out what this acceleration is. Yeah? So how do I figure out the force? I got to go to this problem. This problem, the details they gave me in the first half of the problem will tell me how big the force is, and it will also tell me what the initial velocity is. So I need to figure out my initial velocity and the strength of the force to answer this question. Because once I figure these out, I can plug them into this question. Okay, so let's, I'm going to clean things up here, and then I'm going to move my work here that I talked about down the page so you can see it later. So the information I've been given are enough to figure out what the force is and what the initial velocity is. How do I do that? Well, I don't know what the force is, so I don't know what the acceleration is. But I do know that the acceleration is going to have 0 I hat component and some unknown j hat component. Why is the I hat component 0? I know that the force it feels will be pointing straight down. They gave me a clue in this question and told me, where did they say it? The electric field is pointed straight upwards, and that means the force a negative charge is going to feel is going to be a uniform force pointing straight downward. So I know it's going to have a constant acceleration in the downward direction. The initial velocity, I don't know what the initial velocity in the x direction is, but I do know the initial velocity in the y direction is 0. Now in terms of these two, the position vector as a function of time is going to be, you know, this is the position is is going to be the initial position plus the initial velocity times t plus a over 2t squared. And the velocity under constant acceleration is going to be v naught plus at. You break it down in terms of its x and y components separately. So the x direction, it's going to be, your initial x position is 0. Your initial x velocity is v0. So t. I don't know what v0 is, but I know that the acceleration in the x direction is 0. The initial y position is going to be 0.005 meters. It's 5 meters above. The initial velocity in the y direction is 0, and I don't know what the acceleration is. The velocity in the x direction is going to be constant because there's no acceleration, and the velocity in the y direction is going to be the velocity in the y direction is going to be 0 minus or plus ay times t. Okay, so I'm going to use the fact that I know about where it is. I don't know what time it hits there, but I know that it will hit here. That's where it collides. So at t collision, the x coordinate is equal to 0.3 meters, and the y coordinate is equal to 0 meters. So so in terms of these equations, this one becomes 0.3 is equal to V0 times T collide. And your next one is 0 is equal to 0.005 plus AY over 2 times T collide squared. And what else am I given here? What else do I know? Let's see. I know where it hits. You can only hit it one place. Yes. That acceleration is going to bring it down to that location in a certain amount of time. Yes. Oh, look, it's a 3-ball problem. Okay, let me think about this some more. Usually we're given a little bit more detail. Two plates lie on horizontal planes. Okay. Okay. So I think there's probably going to be some kind of fun proportionality at play here. My guess is that completing this question involves solving for AY in terms of V naught. All right, before I go anywhere, why can't I continue with the information I've been given? If this was a projectile motion question, we'd be fine because we know what the acceleration is. And so if you knew what the acceleration is, you can figure out what your initial velocity is, knowing what your final position is. But because we don't know what the acceleration is, and we don't know what the initial velocity is, you might have ended up at this final location because you started out going slow and the acceleration is low. Or you might end up at this final location because you're moving fast and the acceleration is high. So there's like an ambiguity here. But we're still given a critical piece of information, and I think that you can reason this through even if you don't know what that relationship is. There's some proportionality at play here. So I'm going to continue through algebraically like it's not an issue. So I'm going to solve for AY. AY is equal to minus 0.01 over, oops, hold on. I'm going to solve this one for t, and then I'm going to substitute in. So t collide is equal to 0.3 divided by v naught. And then And now I'm going to plug that into the second equation. So it's minus 0.05 is equal to, should be another 0, ay over 2, 0.3 over v naught all squared, which when you rearrange it becomes ay is equal to minus 0.005 times 2 divided by 0.3 divided by 0.3. So that's minus 0.111 v naught all squared. Okay. Now that I have some sense of the relationship between your initial velocity, which we don't know, and your acceleration to get to that final position, let me double check here. 0.005 times 2 divided by 0.3. Yeah. You can figure out what the final force is for the force that this, what was it? This is an electron, right? Right, so this is an electron. So the force the electron feels is going to be the mass times the acceleration it felt, because there's only really one force on it. So mass electron, so it's going to be, okay, in the j hat direction. Mass electron times minus 0.111 v naught squared j hat. So the mass of electron is 9.11 times 10 to the minus 31 times 0.111. So it's going to be minus 1.011 times 10 to the minus 31 v naught squared j hat. On to the proton part of it. We argued that the proton is going to feel the same force in the opposite direction, so pointing upwards. So it's going to be plus 1.011 times 10 to the minus 31 v naught squared j hat. So we can use that force to figure out what the acceleration is. M proton. So it's going to be 0 in the I hat direction and 1.011 times 10 to the minus 31 divided by the mass of a proton, 1.673 times 10 to the minus 27, which is 6.04 times 10 to the 5 v naught squared j hat. So that's its full acceleration. We don't know its initial velocity. So we know that it has the same initial velocity as the electron in the j hat terms. And so the equation for how it moves is going to be position, initial position is 0. Initial position is 0.005. And then this one is just moving v naught t. And this one has no initial, the z direction has no initial velocity. But it does have acceleration in the upwards direction. 6.04 times 10 to the minus 5 v naught squared j hat over 2. So that's the acceleration over 2 t squared. So at t collide, your x component is unknown, but your z component is equal to 0.01 because it's going to hit the top plate. Okay, so let's put that together. X collide is equal to v naught t collide, and z collide is 0.01 is equal to 0.005 plus 6.04 times 10 to the minus 5 v naught squared t collide squared divided by 2. So I'm going to rearrange this expression. 0.01 minus 0.005, yeah, times 2 divided by 6.04 e minus 5. So it's going to be 165.6 over v naught squared is equal to t collide squared. And I'm trying to figure out what this value is. So I'm going to rearrange that expression for t collide is equal to x collide over v naught. And now I'm going to use this to replace for that. 165.6 is equal to v naught squared, which is equal to x collide squared over v naught squared. Oh, hey, look, the v naughts cancel out. 165.6. Take the square root of that. 12.8 meters. Oh man, this collision happens way further down the line than the first one, than this collision did. And the reason is because the electron is 4 orders of magnitude lighter than the proton is. And so the distance you're going to travel before you accelerate down to that height is going to be, what is that? How many orders of magnitude is that? It's a ways. Anyway, let's move down the line. So that question's tricky. But boy, if you can do that question, you can do anything. And that's also why I did the question for you. All right, so now 23.30. So most of this question, this particular assignment looks really long, but the last bunch of questions are all very qualitative about electric field lines. So it shouldn't be, don't expect it to be too tricky. 23.30. All right, anybody ask any questions? Nobody's asked any questions. One question you could ask is, hey, you just took 45 minutes to do 2 questions. I'm like, yeah, but I'm narrating them. An electron is initially placed 0.1 meters to the right of a small charged sphere. And then this electron is placed right there. And the electron is going to move with an initial acceleration of, it's going to move to the right. .0 times 10 to the 7 meters per second. And so the question is, what's the charge on this sphere? Okay, so this question is way easier than the previous one. Here's the basic principle. This charged sphere is emitting an electric field. This distance here is okay. So this electric field is applying a force to this charge. It's applying a force in that direction. Okay. The strength of the force it feels, this force, depends on how strong the electric field is at that point, and also how much charge is on the electron. Okay? And then once it has that force, because of Newton's laws, according to the inertia it has, it's going to accelerate. So we're going to move backwards through this problem. Knowing what the acceleration is, you can figure out what the force is. Knowing what the force is, you can figure out, using the charge, what the electric field is at that point. And knowing what the electric field is at that point, you can figure out how much charge there is. Does that make sense? All right, let's begin. This one's pretty fun and involves lots of looking stuff up at the front of the book, which when I was a student, I loved. I still kind of love it. You feel very, well, you feel like Doctor Who. It's cool. Okay, so the acceleration is 4.0 times 10 to the 7 I hat. That means that the force it feels is going to be mass of the electrons times the acceleration. So you go and look up the mass of the electron, and it is 9.11 E minus 31. Incidentally, that's why the emergency number in North America is 911, because you're writing down the mass of an electron, which everybody knows. So the force it must be feeling is 3.644 times 10 to the minus 23 newtons in the I hat direction. And if you think about this charge as a probe, you can calculate the electric field by dividing the force it feels divided by the charge. So in this case, it's 3.644 times 10 to the minus 23 divided by the charge of an electron, which is minus 1.6 times 10 to the minus 19. So the electric field at that point is 2.27 times 10 to the minus 4 newtons per coulomb I hat, so minus sign. So the electric field is pointing inwards, which makes sense. An electron is going to be repelled by a negative charge, and negative charges attract electric fields towards them. So there you go. That's what the electric field is. So what kind of a charge would make this electric field? KQ over R squared, 0.1 all squared, is equal to minus 2.27 E minus 4. Q is equal to minus 2.27 E minus 4 times 0.1 all squared divided by 9E9 minus 2.77 E minus 4 times 0.1 times 0.1 divided by 9E9 minus 3.08 times 10 to the minus 16 coulombs. Right? Yep. That times the mass times the charge of an electron So it feels that much force divided by the mass of an electron. Hmm. 1, 2, 3, 4, 5, 6, 7. Yeah, okay. So there was a slight issue with this, which is I think that my calculator messed up the sig figs. But aside from that, that's good enough for now. That's how you do that question. Or maybe there was a slight, yeah, I'm not sure. I got an answer that was wrong by a decimal. So when I check my answer. So be careful about that. Calculators, they make mistakes. They're like humans. All right. Now, next is 24.3. These are 24.3. These next ones are very visual, so they're pretty fun. 24.3 is about electric field lines. Can you draw an electric field line through at the location in space where the electric field is magnitude 0? Can you draw a field line there? That's a great question. To answer that question, we have to think about what the field lines tell us. If you only see one field line in the wild, it doesn't really tell you much, but it does tell you some things about the vectors, right? It tells you which direction the vectors are pointing. The E vector here must point that way. The E vector here must point that way, right? So it doesn't tell you how strong the electric field is, though, right? It doesn't tell you whether it's a strong electric field or a super weak electric field, but it does tell you what the direction is. So you need the other field lines around it to interpret how strong the field is. Now let's suppose there was a point where E is equal to 0. And let's suppose you did draw an electric field line through it. You would assume, based on this line going through this point, that there was an electric field and that it was pointing that way. When in reality, there is no electric field. So you can't draw an electric field line through a point. Yeah. And it's because the electric field lines tell us which direction the electric field is pointing, and if it's 0 electric field, it's not pointing in any direction. All right. 24.20 modified. All right, so it gives you an electric field. Oh no, I drew that wrong. So here's an electric field. And it gives you some regions. And it asks you where the field is strongest. So it says, okay, here is a region. I'll make it 3 long. 3 long and 1 marker wide. And I'll call it, give me a different color pen. I'll call this one A, B, and C. And it asks us, where's the electric field strongest and where is it weakest? Just draw another line in here. All right. Where's the electric field strongest and where is it weakest? Rank them. And so what you can do is you can say, okay, well, how many electric field lines are there in each region? The density of electric field lines gives you an indication of how strong the field is, right? So here, the electric field is strong. Here, because it's got 3 lines going through it. Here, there's barely 2 lines going through it. And here, there's only 1 line going through it. And so, EA must be weaker than EB, which must be weaker than EC. Do you see? It's not rocket science. It's electric field lines. I love electric field lines. This idea that we can kind of do some visual spatial reasoning without having to rely on numbers or words, it's gorgeous. It's a method for us to reason through a problem without having to do any math. I'm not sure if you like that, but I think it's great. Next one is a word problem about closed surfaces and flux. Okay, so closed surface A is a sphere of radius r. Closed surface is B, so that's A. B is radius 2r. And C is a cube with side length r. Okay, fine. At the geometric center of each closed surface is a small ball, completely enclosed by the surface. It carries electric charge plus Q. Okay. Assuming there are no other charged objects inside any of the closed surfaces, rank the surfaces according to the electric field lines, flux through them, largest first. Alright, so when we're talking about flux, what are we saying? We're talking about how many field lines go through them. So this one has 1, 2, 3, 4, 5, 6 lines exiting. If in the other diagrams, there's the same number of lines per charge, so 6 lines come out of each. This one has 6 lines leaving it. I guess I didn't draw the arrows. For a line to leave, it has to pass through one of the surfaces, right? And the last one has 6 lines leaving it. And no matter what kind of shape I enclose the charge with, those 6 lines have to pass through it. So they all have the same flux. Ta-da! Alright, that's it for online office hours this week. If you have other questions you'd like to see me do from this next week's assignment, go ahead and ask. Or rather, send me an email with the question you want me to ask. And then, otherwise, have some fun with this. This particular assignment, it's a little bit hairy at the start, granted, but the last part of it is very liney. I really want you by the end of the week to be pretty strong with Gauss's laws. So next week's assignment is going to be based on Gauss's laws, and let's see, when's our midterm? No, I didn't write. Did I write the midterm on there? I wrote the midterm over here. Yeah, so our first midterm is going to be based on everything up till Gauss's laws. Stuff we covered this week, and then, how should I put it? Okay, so the first, here's a side note. In the courses you take, when you're writing a midterm, unless your prof is bonkers, they're going to be focusing on the material. When they write the midterm, they're going to be focusing on the material that you've already had an assignment on. So our last assignment before the midterm is a Gauss's law assignment. And that means definitely Gauss's law stuff on the midterm. The stuff after, so the cutoff for the midterm, I guess, is probably going to be next Wednesday, which will take us past Gauss's law into work and energy in electrostatics. But since I won't have a chance to give you an assignment on those particular questions, they'll probably, any of that material that shows up will probably be fairly generic, kind of like the clicker questions we'll do in class, or like the activities we do in class. so they won't be all that deep. Whereas you'll already have an assignment based on Gauss's law and all those classes in that workbook. So I definitely am going to assume that you know your way around Mr. Gauss. Anyway, have a nice day. Enjoy your assignment and stuff. See ya.